Okay, one, two, three.
Hey there! Do you know what cable television, CT scanner, rainbows, and atomic waves have in common? Well, they all follow the same principles of electromagnetic radiation. And in this video, we're going to talk about what it is. Say we have a particle. When this particle is in constant motion, it will generate both electric and magnetic fields, thereby producing electromagnetic waves. These electromagnetic waves then propagate, thus transfer energy from one point to another. This process of transfer is called the electromagnetic radiation. The waves of electromagnetic energy traveling around the globe and throughout space make life on Earth possible. EM waves can travel in a vacuum. Thus, it does not need any specific medium to transport. In a vacuum, it travels at a speed of light at around 300 million meters per second. Light itself is just a form of electromagnetic radiation. Other forms of electromagnetic radiation are radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays, and all of these can be seen at the electromagnetic spectrum. Have you ever wondered what type of waves are used in your radios, televisions, and remote-controlled toys? Well, if you're thinking of radio frequencies, you're right. Radio waves are known to have the longest wavelength, the shortest frequencies, hence the lowest energy in the spectrum. Each wave can range up to a length of a football field to a length larger than the diameter of Earth. Radio waves are generated by time-varying electric currents in a metallic conductor, or what we commonly know as the antenna. The antenna is firstly applied with an oscillating voltage which will generate an oscillating current. Due to this oscillation, the electrons in the antenna move back and forth on its terminals. This regular motion of the charged particles causes the emission of radio waves. Radio waves may then be propagated from the transmitting antenna to the receiving antenna through or along the surface of the Earth, through the atmosphere, or by reflection from natural or artificial reflectors. Radio frequencies are subdivided further into what we call as bands, and these bands are utilized in different types of applications. So thanks to radio waves, humanity has given birth to wireless telegraphy and modern forms of telecommunication. Following radio waves in the EM spectrum is my favorite wave. It's what I use to reheat my favorite dessert, Krispy Kreme donuts. Again, you're correct, these waves are called microwaves. Microwaves are basically high-frequency radio waves, but they are distinguished from radio waves because of the technologies used to access them. For example, in a mobile phone, they are made by a transmitter chip and an antenna. In a microwave oven, they are made using a magnetron. In a magnetron, a heated cathode is surrounded by a ring-shaped anode. The anode has cavities cut into it, and a magnet is placed under it to generate a magnetic field along the length of the tube. Upon switching it on, the electrons would boil off from the cathode to the anode, traveling through the electromagnetic field. As the electrons nip past the cavities then emit the microwave radiation. But microwaves are not only used in heating food or making calls. It can also be utilized in weather forecasting. Microwaves that penetrate haze, light rain and snow, clouds, and smoke are beneficial for satellite communication and studying the Earth from space. As you can see, this image is generated using radial pulses in the microwave spectrum, allowing humans to monitor weather conditions. The next EM wave is considered to be the most special of them all, as it is the only one that human eyes can see. And these waves are called the visible light. Visible light constitutes tiny packets of energy called photons. Photons are the fundamental particles of light. They have no mass, they carry energy, and they act both as a wave and a particle simultaneously. At microscopic level, visible light is created when an electron within an atom is in an excited state, drops to a lower energy state, and loses its excess energy. The same way, incoming light can elevate an electron to a higher energy state by being absorbed by it. So what will happen if visible light spectrum did not exist? Well, this will happen. Black is the absence of the visible light spectrum, and that would be sad. The next EM wave is X-rays. So whenever you hear X-rays, what comes first to your mind? Is this right? Some of you might have experienced getting into a laboratory room and you have to hold your breath for this picture to be captured. To walk you through how this works, we must first know that X-rays are also composed of tiny packets of high-energy photons. To make this radiographic image, an X-ray beam is used, which is composed of millions of X-rays. These X-ray beams are produced by an X-ray tube assembly by accelerating electrons through a potential difference and directing them onto a target material. These beams are created isotropically, which means they diverge equally in all directions. This is why an X-ray tube assembly requires protective lead housing that absorbs the extra X-ray photons to protect other people from unnecessary radiation. This directs the beam directly to the patient to produce the radiographic image. Now for the last EM wave. Do you know what this is? It's a star exploding. When violent reactions such as this happens, gamma rays are emitted. Gamma rays are the most energetic form of light, and it's even the most powerful. Gamma rays are the very highest energy form of that type of radiation. A single gamma ray photon is more energetic than 1,000,000 visible photons combined. They are energetic enough to break apart atomic bonds. Gamma rays are also penetrating that they can damage our living cells. However, they can also be used in beneficial applications such as radiotherapy, sterilization and disinfection, and the nuclear industry. Artificial sources of gamma radiation are produced in fission in nuclear reactors, high-energy physics experiments, nuclear explosions, and accidents. So that would be all about electromagnetic radiation. So I hope you learned a lot. Don't forget to subscribe and give us an A. Give us a like. Thank you. See you once again in our next video.